Hello everybody, this is video 4.1. We're going to be starting multiplication and talking about ideas around multiplication in this chapter. So this section we're going to be looking at basic interpretations and building some basic models around multiplication. So let's get started. So the first thing we want to define, we have a lot of things that we need to define for this chapter, but first thing we want to define is what multiplication even is. And so you can see the definition that we have, that multiplication is the sum of a number of equal sized groups. So the fact that we're using the word sum should be an indication to our students and as a reminder to ourselves that multiplication is in a lot of ways an extension of addition. So let's look at an example. If we were to write 5 times 3, we want to be really careful with this because a lot of times what people will say is that, well, this means that I'm adding 5 3 times. And so some students will misinterpret that to mean 5 plus 5 plus 5 plus 5 because they're adding 3 times. And so if we say this in kind of an unclear way, then we're not really being very precise about what there is 3 of. It's not that there's 3 additions, is that there's 3 fives that are being added together. So it is the number of the groups, not the number of additions that are taking place. So this is not correct. We want to get rid of that. So we want 1, 2, 3 fives. That's what's being added together, and so we get 15. So you've probably been multiplying mathematically for a long time. It's kind of hard sometimes to give a definition for something that you've been doing for so long. You think about it very innately and very intuitively, but keep in mind for a lot of your students, this is not the case, especially if they're learning it for the first time. And so giving them a weak definition of what's taking place kind of sets them back in their learning. So we have a really good definition of what we mean by multiplication because it is such a fundamental and foundational operation. Anyway, so the product, so we've done multiplication. So the product is the answer to our multiplication problem. So in this case, the product would be 15. The factors are generically what we call the numbers that we're multiplying together. So in the same way that we call the things that we're adding terms, the things that we're multiplying, we generally just call factors. Now, there are more specific names to this. The multiplicand is the thing that is being multiplied, and then the multiplier is what it's being multiplied by. I don't know that you're going to hear those two terms an awful lot. So, I mean, just know that those terms exist, know that there are names for them. This is probably going to be the last slide in which I use either of those two terms. So, factors is the more generic and sort of broadly used terms. We're going to see in a little bit that because we have commutativity, we can switch the order around. And so your multiplicand and your multiplier have very limited context. Those two, the distinction between those two terms will be useful for a very short time, and then they'll just sort of move on to just sort of generally being factors. So know that these terms exist, know that these two things have different names, but just know that they're not going to come up very much. So we can talk about this as repeated addition. And so we've already seen that 5 times 3 means that we're going to add 3 fives. And as I mentioned in the previous slide, that we have this sort of specific context at the beginning, that we want students to think of this as 5 taken 3 times, or 3 sets of 5. Be aware that a lot of books, especially when you're first introducing this topic, are really strict and really precise about this. And that if you have 5 times 3, they want you to write it as 5 plus 5 plus 5. Or depending on how they sort of like have the context, they might have it as 3 5 times. But usually it's the first number is the set, and then this is the number of sets. And so typically this is what you're going to get, that this 5 times 3 would be 5 taken 3 times. Now, we can extend this now to say 3 times 5 would be 3 plus 3 plus 3 plus 3 plus 3. So we do want students to sort of understand that there is a distinction from a model standpoint between 5 times 3 and 3 times 5, even though mathematically we're going to see that they come out to be the same thing. But we want them to sort of understand these two, that there can be a distinction between the two, which is kind of weird because eventually we're going to kind of like lift the veil on that and say, not really. But this does help us to understand how students can build their understanding around what multiplication is. You argue the relative merits of that if it's a good use of your time and of students' learning time, but just be aware that this does come up in a lot of books, and a lot of teachers are really kind of specific and territorial about this idea, this model of multiplication. What we're going to get to eventually is that 3 times 5 and that 5 times 3, that if I put these things together, so let's say that 5 times 3 means I'm going to take 5 3 times. And so I'm going to build this as a little set model. So here's my 5 taken 3 times. So 5, 5, 5. And then I could also do 3 times 5, which means I'm going to take 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And the punchline for this is that the way that we arrange these things, that if I do my 5s as horizontal bars stacked vertically, and then my 3 as vertical bars aligned horizontally, that these will, and these are all 3s here, which I probably don't need to write, but I'm going to write anyway, that these will eventually sort of collapse into this rectangular model. One, two, three. And so from this, we can kind of see, here's my 3 groups of 5, and then here's my 5 groups of 3. Oop. So 3 times 5. And so once we have this rectangle, then we can kind of see both models at the same time. So we don't need to have that distinction. So we have this model that allows us to see both models, and then once we have both models sort of collapse into one thing, we're just going to use that one model. So it's there if we need it, although realistically we're not going to need it that much. But it does help us sort of build to that. And as we'll see here in a couple of sections, I think section 4.3, that it allows us to very quickly and very succinctly show the commutative property for multiplication. One of the things that we can use to show multiplication is this thing called an ordered pair, or what you might have seen as sort of a tree model. One of the things that's interesting about multiplication is that our elements can mix. So, for example, if I were to say 3 students have 6 pencils each, then we understand that this problem would be something like 3 times 6. So these 3 students each have 6 pencils, so we're just going to multiply that 3 times the 6. But if we were going to do a problem like 3 students plus 6 pencils, we have no idea what that means. So in addition, because we're adding the same type of element, a problem like this isn't going to make an awful lot of sense. In multiplication, though, we can mix things together. So if we take an example where suppose we are getting ice cream, and we're getting ice cream on a cone, 1 scoop of ice cream on well, just 1 cone. That'd be kind of silly to have 2 cones. So we're going to have 3 flavors of ice cream. So we've got 3 flavors. So we're gonna be kind of boring here and just go chocolate. We're gonna go vanilla, and we're gonna go strawberry. And I'm using W for strawberry for reasons that'll be obvious here in a moment. And then we've got 2 cones. So we've got our regular and our sugar cone. So there's the S for sugar instead of S for strawberry. I could have gone either way. It is this. that's not the point of the problem. So we've got a couple different ways of doing it. So we're going to select our cone first. And so we're going to do our cone. And so I can either pick a sugar cone or a regular cone. And then after that, I'm going to pick my ice cream. And so I could go sugar cone with chocolate, with vanilla, with strawberry. I could go regular cone with chocolate, with vanilla, with strawberry. And so I can see this is 2 times 3. This is 2 different cones, 3 different flavors, and I get 1, 2, 3, 4, 5, 6. And so 2 times 3 equals 6. Now, depending on the type of problem that you're doing, this model might be more useful. It might not be as useful for some of the things that you will be doing potentially with probability and having students sort of see the full scope of all the possible outcomes. A tree diagram works really well. This idea of an ordered pair, that I could have sugar, chocolate, that I'm picking the cone first and then the ice cream second. So I couldn't pick chocolate sugar because there's no chocolate cone, there's no sugar ice cream, although all ice cream is essentially sugar. That these things, it adds a layer of complexity that you may not use in the earlier grades. This is going to be probably a lot more appropriate for the higher grades where there's a reason you're using this model. There's greater mathematical and pedagogical implications for why you would want to use a model like this. So we're not going to look at this model an awful lot, but just know that it's there. There's other models we could use for multiplication, but this rectangular array is where we're going to live most of the time. So we can think about now extending this to multiplying by 10. And so we've looked at already sort of basic problems in multiplication, but now we have this special case of multiplying by 10. And a lot of students that have seen multiplication before will already know that multiplying by 10, you just quote unquote add a 0 to the end. And that might be how you think about it as well. And mechanically, I mean, that's true, but conceptually what's going on with adding that 0 deserves a little bit of attention. So let's take a problem like 3 times 10. And we've already seen from the previous slides, the previous section, that we can think of this as 10 times 3, and both of these sort of yield this rectangular model. So we'll do this as 10 this way, and now we'll break this 1, 2, 3. So there's our 10 by 3. But we think about this in terms of our base 10 blocks. This is really the same as just taking 3 longs. So this should translate to just being 3 longs, and then we know that this is a 10, this is a 10, this is a 10. And so when we're multiplying by 10, what we're effectively doing is we're taking every piece and we're trading it up to the next size piece. So these ones, or these units, get traded into these longs or tens. And the same thing would apply that if we had tens, they would get traded up into hundreds, that the hundreds would get traded up into thousands, or in the language of base 10 blocks, that my longs get traded into flats, and my flats get traded up into blocks. Now, trading into blocks is a little bit more complicated because now we're moving beyond an area rectangular model because the blocks are inherently three-dimensional. But if we've developed this language and we've developed this model around base 10 blocks, then explaining why everything sort of moves over one place value makes sense. And then once everything moves over a place value, we've talked about the 0 before, then the 0 filling in that far right spot is no longer the entire method, but is a natural result of understanding the process of what's happening when we multiply by 10. So rather than it being just add the 0, we understand that the pieces move and that the 0 becomes a necessary consequence of moving everything over one place value. So this 3 that we had in the ones place moves over into the tens place, and then we fill in those ones. Is it possible to have any ones after multiplying by 10? If we're multiplying a whole number by 10, no. I mean, if we're multiplying by a decimal, we could. But multiplying a whole number by 10, which is kind of what we're talking about in this section right now, then no, we're not going to have any 1. So we know that 1's place is going to be held by a 0. So rather than put that 0 at the beginning of the method, we want to make sure that it's motivated by some sort of model, by some sort of thinking about what's going on. So we have our checkpoint problem. So I want you to think about modeling 12 by 6 and how you would solve that problem. And then I want you to think about how you might model it a different way and solve it. Now, how are these two solutions similar? Obviously, the two solutions will be similar because they'll be equal. You should get 72 in both cases. So not looking for how they're numerically similar, looking for how they are maybe mechanically or conceptually or visually similar, but then also how are they different. And so this is going to vary depending on which models you use, but think about how they're similar and how they're different. All right, thanks everybody.